Oh, that was loud. Oh, yeah. Oh, wow. Crazy. All right.
Can you guys hear me? Can you hear me whispering?
Forget it. Starting over. Okay, here we go. What's up, everybody? Welcome to my channel, Behind the Code. My name is Jerry, and today's video, we're going to be looking at the HD44780 LCD displays and the standard protocol that goes with driving these. For those of you that have been curious or maybe have messed around with microcontrollers to drive these, so you might have used like a PIC microcontroller or an Atmel microcontroller, there would be a library that you would get that you could use with the code to drive this. So you could just, simply enter in one command and, say print such and such, and it would display it on the screen after you've connected and interface it using the basic standard interface to the Databus and the driver pins. For me, I thought that was great, but for me, I found it really agitating that I didn't know actually what was happening in terms of the protocol and the signals that were going on with these, and how the signals work, how the logic worked. And so essentially that's what this video is about today. I'm going to be showing you guys the raw digital logic, the protocol that's used to drive these. It's called an HD44780 LCD display. Doing that is a bit dry, but hey, I think it's cool, it's awesome. I love that, the VHDL code and doing digital logic projects. And so probably the fact that you're here, you do as well. So let's get to it. All right, here we go. Okay everyone, so welcome to my instructional video on driving an HD44780 LCD display unit. What I'm going to be doing for this particular project is I'm going to lay out everything step by step so that you can see how the VHDL code creates the necessary signals and the timing requirements in order to display information on the screen. Different characters, numbers and letters and whatnot. And eventually I might get into showing you how to create your own custom fonts that you can program into the LCD display and essentially create your own fonts or graphics essentially. But that will be a later video that I'll prepare. But for this particular series, I'm just going to start out by showing you and explaining the concepts of how the HD44780 LCD display operates and the signals that are required to initialize it and then to send specific data on the Databus to display specific characters. So I know a lot of the tutorials that are out there are either for microcontroller based different components, but for mine I'm going to be showing you how to do it using an FPGA and VHDL code. So I've chosen to use the Altera DE2 board, and I'm sure some of you are either used to using the DE1, which is another popular unit. And so this is a picture of it here. This is the DE2 board, and the reason I've chosen to use this particular unit is that it already had a HD44780 LCD display interfaced as part of the development board. So now we're going to be going through the VHDL code as well. I'm going to be taking you through that step by step, and I will provide it for you to download, and then you can try and manipulate it and enter in your own characters and essentially see how the VHDL code is implemented and how it operates to display data onto the display. So now I'm going to bring in an image here of the LCD display. So this is the one that we're essentially going to be using. This is the 16 character by 2 lines, so 32 characters in total. And there are different ones that you can get. but they all operate basically the same manner. So here's another unit that's that you can get. And these are all usually available on eBay fairly cheap, within $5 or so, and they're all interfaced in the same manner. And I'll bring in a couple of other shots of different units that you can get. So there's 20 by 4 LCDs, there's 16 by 2, there's 128 by 64, and so on and so forth. And they all basically operate in the same way. But for this particular tutorial, we're going to be focusing on the 2-line 16 character LCD display. And so, and once you get that, you can move on to further trying out different screens if you wish. So anyhow, I'm going to bring in the interface for this. So essentially here we have our interface lines. We have our VSS, which is our ground. We have the positive V voltage. Then we also have our contrast voltage, which is essentially a specific voltage level that you can dictate through a resistor, essentially to dictate a voltage divider to provide a specific contrast level on the screen. And then we also have our register select, our read and write enable, and then our Databus. And then we also have our backlight voltages and ground. So the main ones that we're going to be focusing are the Databus, so data D0 essentially all the way through to D7 for our 8-bit Databus. And then mainly we're going to be looking at is the enable line and also our register select. Those are the two most critical lines that you have to worry about, which essentially will dictate where and how the LCD display will interpret the information that you're sending to it. So anyhow, what we're going to be, what I've done is, I'll show you an image here. What I've done is I've actually interfaced my logic analyzer. I have a Tektronix logic analyzer module, and what I've gone and done is I've interfaced directly to the Databus and to the control signals, and I've produced this VHDL code which we'll be reviewing, and it produces a message on the screen showing a Bluetooth link on the first line, and then connected on the second line, all in capitals with a little arrow font. And what we're going to be doing is we're going to be looking at how this particular LCD screen, the HD44780, is initialized, and then how the data is sent through on the Databus to display this message. So we're going to be going through that step by step, and then what we're going to be doing is looking at the logic waveforms essentially of how this is produced and how it's initialized and how it is displaying these characters on the display. And so we're going to be able to look at that. So it's, as opposed to looking at a simulation through Model Sim or another simulation software, we're actually going to be looking at exactly the logic signals of what our VHDL code has produced. So it's a real asset to actually see the true logic waveforms that your code is generating. So this is the message that we're going to be looking at, and what I'll do is I'll show you the process too. I'm going to switch to my my GoPro, and I'll show you guys how I've hooked it up and talk about my logic analyzer there briefly, and then we'll run through our program, our VHDL compilation that I've synthesized, and we'll program the DE2 board with this particular message, run the scan, and then we're going to go and look at the waveforms, and we'll review the waveforms, and I'll explain what the signals are, how they're generated, and what it's doing. And once we review the waveforms, then we'll go and we'll review the logic code so that you can see the VHDL code and how it was written. And I'll go through that line by line, and then we can see how it creates the specific output waveforms to drive this HD44780 LCD display. Okay, so essentially what I've got here is I've hooked up my Tektronix TLA 7000. This is the TLA 715 logic analyzer, and I've got it interfaced to an expansion box, which is the TLA7XM. And essentially what that does is the standard portable TLA logic analyzer is only able to accommodate up to 2 modules for interfacing various either whether it's a digital oscilloscope module like I have here, or the logic analyzer interfaces, or you can also have pulse generators for different applications when you're testing digital circuits. But anyway, just to explain my setup, so essentially this is just a standard logic analyzer interface from the TLA 715 logic analyzer mainframe, and I've got all my cable lines here, and we're only going to be using various signals to monitor the databus, the 8-bit databus coming off of the HD44780. That's the digital displays, the LCD displays rather, that we're discussing here. And so essentially what I've done is I've soldered on a header here for us to connect to, and it allows me to interface my probes from the logic analyzer comfortably. So essentially what this is going to allow us to do is to monitor and view our logic signals that are being generated rather from our VHDL code, and so then you can see the waveforms on a timeline and compare that your actual waveforms being generated from the VHDL code, so you'll be able to see it a little more rather than just in theory or simulation within model sim and whatnot. So this is a really good exercise, and it allows you to see the actual code as opposed to just the simulation. So what I've done is I've set up, and I'll show you here now. So I've got my keyboard here that's hooked up, and I've set up the logic analyzer for various triggers. And what I've done here is I've got it triggering on a group value. So essentially the databus, I'm monitoring the databus, which is on my probe setup D3, and that's essentially this group here, and I'm monitoring the 8 signals on that as the databus, and these are interfaced to D1 through to D7, D0 through to D7 rather, the 8 bits are databus. And then on my D2 probe, I have the control signals. So I have our RS, our RW, our enable, and we can monitor all those and view those in relation to the databus, and we can view that simultaneously on our waveform. And so I've set that up, and what I've done is I have it so that the trigger for this is going to be a hex value of 38 on the databus, which is essentially our first command, or our first value that we send on the databus as part of the initialization of the LCD display. And so now I'm going to activate the power on our Altera DE2 board, and so there you have the standard welcome message. And right now it's going to be monitoring the databus, our 8 bits, and it's going to wait to, once it detects a hex value on that databus of 38, it will proceed through and capture and then display it on the screen for us. So what we're going to do now is actually set up the run sequence for the logic analyzer. So as soon as I hit run here, so there you can see it's starting. Now it shows here running. So now it says stop because currently it's scanning the 8-bit databus right now. It's in the middle of scanning that in real time, waiting for that hex value of 38. And because our Altera default display here has run through its sequence already, because I powered it up beforehand, and so there's no values being shown or being read on that 8-bit databus. So it hasn't been able to see any value there, and that's why it's continuing to loop in its run sequence, constantly capturing, waiting for that hex value of 38. So now I'm going to go and run through and program our Altera DE2 board with our VHDL code that I put together to drive this LCD display. And once I'll come back and I'll show you that, and then we can go over the VHDL code and I'll explain that in a step-by-step sequence of each line of code so that you can understand the relation to the waveform. So I'm going to go over there now and run that sequence. We'll just go by the lab here, and this is the setup I have, and there we have the Quartus programming setup and our VHDL code. And here's the VHDL code sequence that I have here, and we're going to be going over that line by line. Right now it might look a little complicated, but I'm going to be explaining that in the video. And so anyhow, we're going to go ahead and program that. So right now we're going to run the programming sequence, and then we're going to go and view it. So I've hit start, so it's run there. It has just programmed our Altera DE2 board, and now it should already have stopped and run through the sequence. So as we'll go over here, you'll see that it is now completed, and now it went from the stop menu and now it's on the run because it's completed and it's already done its scan. So now we're going to go and view the waveform that it's captured and view the data. And what I'll do is I'll do a screen capture so that we can see it a little better in the video, and I'll overlay it as I go through and describe it. Okay, so we got lots of displays. These are displays you guys are going to be displaying characters on and doing cool interface projects. How are we doing? Find it interesting? Is it good? Hit the like button, please, and subscribe. Quick! Okay, so we've just run the scan of our VHDL code file running, and again displaying the message Bluetooth link connected. And that's essentially what we've done here. Is we've run the scan off of from the logic analyzer, and we're going to be able to monitor these signals, and I'm going to discuss the signals and how they function to not only initialize the LCD but also to display the message on the screen. And so we'll talk about that now. So essentially what we have here is we have our enable line right here. So this is a single bit logic line, a single wire. We also have our read and write line, which we don't really focus on too much because it's always going to be on a logic low level, because we're essentially all we're doing is writing to the LCD display. We're not doing any read functions. Then we have our register select line, which again is another a bit line, so it's a single wire, and we're sending it in a logic high or a logic low state. We also have our VDD, which we don't really focus on, and then we have our 8-bit databus. So D3 here, that's the databus that's essentially interfaced to the LCD display, which is data line 0 all the way through down to D7. So 8 specific lines there that we have, an 8-bit databus. And these numbers here are the hexadecimal representation of that databus. So just keep that in mind. So these lines here are single bit values, and then our D3 line here, this is our databus. So just keep that in mind. So now I'm going to explain the signals here, that what we have and how it all works with the HD44780 LCD display unit. So again, so essentially the way it works is this particular LCD display, on the back of it, if I can get a shot of that. So I'm going to bring a shot of that in here. So here we go. And so essentially we have a series of controllers, microcontrollers that are embedded inside of this LCD display on the back, and they respond to a specific set of signals and initialization signals that we send to it, and then it essentially will turn and create the necessary logic signals to actually drive the LCD display. So it's we're already one level in a higher level language, but essentially that's how it works. And you'll get different display modules that'll they interpret specific driving signals, and usually they're all laid out and described within the data sheet for that particular LCD display. So for this one, the HD44780, I'm going to talk about that and the initialization sequence for it. So I'll bring in a set here which just sort of lays out how it all works in the hexadecimal values, and I'll talk also about the enable and the RS lines and how they function. So as you can see here on our logic scan of our message that I showed you earlier, which essentially what it's doing is it's this whole sequence here produces the text Bluetooth link connected on the screen. So just reference that again. So, and then I'll describe it here and you'll see how it all works. So essentially you have your enable line and your RS line that you have to worry about, and the data bus. Those are the ones we're going to focus on. So during the initialization sequence of the LCD display, the RS logic line is in a logic low state. So that's where you see it here. That's essentially all these values here on the hexadecimal, on the data bus, represented in hexadecimal code. Those particular signals that are being sent to the LCD display are all part of the initialization sequence. That's where it has an RS value of logic low. And then the actual signals are read by the LCD display every time the enable line goes from, produces essentially a falling edge. So when it goes from a logic high state to a logic low, the LCD display will read the data on the data bus and interpret that as a specific initialization step through the sequence for initialization. So the steps that are involved through the initialization sequence, we have essentially 1, 2, 3, 4, 5, 6, 7, and 8. Essentially 8 steps within the initialization sequence that are all part of the initialization for the LCD screen. And I'll talk about those 8 steps right now. So our first, let's talk about the first 3 falling edges, and the values that are being sent to the screen are all value 38. And so those first 3 values of 38 in hex that are being sent on the data bus are all part of an external reset function. And so when you boot up the unit, if you've read through the data sheet for it, you'll read about an internal reset or an automatic reset that happens when the unit is booted up. But doing an external reset essentially just guarantees that that your LCD display is ready to receive commands. So that's what these first 3 hexadecimal values of 38 are essentially dictating a reset. So on the 4th falling edge on our enable line, that is interpreted as a function set. So the function set, depending on the hexadecimal value that you send to it, it's waiting, that value dictates how the screen is set up and interfaced. So when we send a value of 38, we're actually initializing the LCD for an 8-bit data bus or an 8-bit transfer. And also we're telling it that we want to use both lines on the display, so the first and second lines. And also we're telling it that we want to have the font size set up to be a 5x8 pixel grid. Now you can, depending if you change the value from 38 to a different value, you can actually tell it and say that you're not going to be using an 8-bit interface or an 8-bit data bus, you're going to be using a 4-bit data bus, and you're only going to be using the first line on the LCD display, not both. And you can also tell it that you want to use, say, a 5x10 font size. So, but for our purpose, we're sending it the value 38, which again initializes the LCD for the 8-bit data bus, both lines being used, and the font size is 5x8. So that's our fourth command within the initialization sequence. That's when RS logic value is in a logic low state. So moving on to the fifth command. So here we have 1, 2, 3, 4, 5 right here. So now when you see the falling edge on the fifth command, our Databus hex value changes from 38 to 08. And so 08, what we're doing is we're telling it that we want to shut the screen off. And so if you were to go and change that value from 08 to a different value, like here for instance, a value of 0F, you would be telling it that you want to turn the display on, turn the cursor on, which is the little, you can have it turn on and showing the cursor, and also you can control its blinking. And that's what this 0F value would do, is it would actually show you the cursor and it would cause the cursor to blink. And so there's different values based on the values that you send to it at different points within that initialization sequence. You can dictate different characteristics of what is shown. So for our purpose, we don't want to turn the display on at all, so we're not sending it a 0F, where we want to just shut it off while we're getting it initialized. So we're sending it a value of 08 in hex, and that will shut it off. And so now the next step, the next programming step in the sequence for initializing is a value of 01. And so what the 01 value does is it clears the display. So that's just straightforward. That's a value of hex 01. So we're clearing it. Then after we've cleared it and gotten rid of any residual data that was on the bus by possibly if you were running it before, you're just making sure that it's been cleared. Anyhow, so then the next step of the sequence that we have is 0C. And 0C hex value essentially turns the display on and initializes it with turning the display on. And if we were to send it the value 0E, for example, you would turn the display on, you would turn the cursor on, and have the blinking off. So there's different combinations that you can have. Like we had here, we had it as 0F, which actually turned everything on. So just remember that. But for our step, we're sending it a value of 0C. Now the last step in our initialization sequence is a value of 06. And what that does is it sets the mode, the write mode, for the display, and how the information that we're going to be sending to it, the character information on the data bus, how it's going to interpret that and what it will do with it. And so that's this last step within the initialization sequence. And so with a value of 06, we're initializing the LCD to automatically increment the address for the display. So it's going to automatically do that for us for every character that we send it. And it's also going to move the cursor to the right. So essentially every letter that we put on, when we go to send it another one, it's going to push the other cursor to the right so that it won't overwrite over top of the character that we've just sent it. So that's what this 06 hexadecimal value is for. And so that being the last step in our initialization sequence, you'll notice how all of a sudden our RS line, or our register select, switches from a logic low to a logic high. And what that does is it dictates to the LCD display that we're now going to be sending it information on the data bus as character data. So it's no longer commands, it's information to display on the screen. So what we're going to do now is I'm going to bring in the chart that I have, and I've displayed the hexadecimal equivalent of the upper and lower 4 bits to explain it, just so you can get a little bit of a better picture on how it works. So for instance, we have all this information here because we're in a logic high on our RS value. With every falling edge on the enable line, that's essentially sending a specific character to the screen. And because the way we have it initialized, every the falling edge of the next cycle, it'll automatically push the character that we sent to it to the right and allow us to essentially display a message on the screen. So now you can see it here where our RS line is in a high state all the way through here, all the way down until the end of this Databus value, hex value of 20 for 2 falling edge cycles. And so what that means is that this entire sequence here is character data, and essentially what this is doing, all of this hex value data on the Databus is essentially displaying the word Bluetooth link on the screen. And so now essentially how that works is we have, so every falling edge on the enable line, it's essentially writing a character. And so if you can see that here, the hex value 42, that corresponds to the capital letter B. Then we have 6C, that corresponds to the letter L, and so on and so forth. And then you can see here how we have 2 values of 6F. Well, if you can see it there, that's because we have 2 lowercase letter O within the word Bluetooth. So that's those 2 values here. And then we have 74, 68, 20, 4C, 69, 6E, and that essentially is writing the rest of the first line. Now you can notice here how in between Bluetooth and link we have a blank space here. Well, that's the value 20. So 20 is your essentially a blank space between words. So you have 20 here, which is the space between Bluetooth and link, and then we have the last 2 characters on the line here after link, which dictates the end of the first line. And so now you'll notice too that the control signal switches from the RS line switches from a logic high to a logic low, and then we're essentially writing a value which is a control signal to the LCD display to give it some instruction on what to do next. And so essentially what we're doing is we're telling it to move with the value CO on the Databus, but as a command to the LCD display, not character data when it's in a logic high state. The RS value is a logic low, that's instructing the LCD with a command on how to interpret the information on the Databus if it's receiving it. And so what we're doing is we're instructing it with a value of C0, and a C0, if I'm going to bring this in here, this little chart here that I have, C0 is a set DRAM address, and what that is that places the cursor at the start of the second line. So essentially what we're doing is we're telling the cursor to carriage down to the second line, to the beginning of the second line. So that's what this CO hex value does when we're sending it when the RS value is in a logic low. And then you can see here, you're probably getting a clear picture of what's going on here. And I'll switch over here 1 second. So there's a little bit more of a zoomed out image there. I'll just zoom in here a little bit so you can see. And so bringing this back in here again, pardon me, I'm getting my images mixed up here. So with the message Bluetooth link connected, and then again with our control signal here, the CO, which is a command telling it to bring the cursor or moving the cursor down to the beginning of the second line so that it starts at the beginning here. Then we alternate again from the control line being our RS line. It switches again from a logic low to a logic high state, and then we have the value 7E being on the Databus, a hex value of 7E, and that is this character here, which is a little arrow. And then it proceeds through the rest and all the way through, and you'll notice here how 20, remember how I indicated that 20 was our blank space? Well, we have several 1, 2, 3, 4, 5, 6 blank spaces on the bottom line. And then if we count our enable falling edges here, when it's on the hex value of 20, we have 1, 2, 3, 4, 5, 6 falling edges with a hex value of 20, which corresponds to our 6 blank spaces here on the bottom of the screen. Then you'll notice where we switch again from our RS value, our RS line here, switches from, once again, it switches from a logic high, which is being a representation of character data on the data bus, is being interpreted as character data. We switch to a logic low, which then again it becomes a command sequence. So then it reads the data on the data bus and interprets that as a command function. And so the command function of hex value 80 on our little my little Word text document here that I created, the hex value, I'll put it up here just so we can see it a little better. And so here we go, we have the hex value of 80. That's telling it it's a set DD-RAM address, and what it's doing is it's placing the cursor at the start of the first line. So now that is interpreted to essentially bring our cursor back to the beginning of the line, right here at the start where capital B is. And then you'll notice again, all of a sudden it switches from that logic low on the RS value to a logic high. So all of a sudden we're back into the mode of sending character data to the display. And so it all of a sudden you see 42, 6C, 75, 65, 74, 6F. Now, if you recall, that is the same value. So 42, 6C, 75. If we scroll back here, you'll notice it here. Here we go. 42, 6C, 75. So essentially what it's doing is it's looping. So it's gone through that sequence, and it's just going to continuously loop. The code is going to continuously loop, constantly displaying this message on the screen over and over again. And now what that means is that it's essentially monitoring the data bus here. And so if we were to actually go in there, if we could go in somehow and manipulate our signal lines or variables, if you will, that are holding the information for specific characters when our RS value is high, if we could manipulate these at different points, we would essentially be able to change the characters that are being on the screen. And so essentially that's exactly what I've done. I've gone and the signal lines or variables that I have set up that dictate which hexadecimal value is here is essentially dictated by either a string value that we can write in within our VHDL code, or also what you can do is have it so that a specific set of switches that you have on your DE2 board, for instance, if you have an 8-bit, say for instance the first 8 bits of switches, you could essentially dictate which hexadecimal value is on the data bus at a particular time. And so you could essentially control what letter is being driven onto the screen at a specific time. And so we're going to go through that, and when we're actually looking at the VHDL code, you'll understand and you'll see how it all works. And so I'll bring in this this chart here that I've created just so you can see it a little better. And I've got the upper and lower bits, and for different hex values that are shown, you can interpret them and find them on this grid here. And this is the chart that's available within the data sheets that you can go and check out. So for instance, for the value, if we go to the beginning of our sequence, so I'll go back to the first page that we had where it shows the beginning of the initialization. So for instance, the value 42, when it's in the RS value is in a logic high, so that is character data being sent. So the hex value 42, let's look at what that is. So if we start with the upper 4-bit, so we got 4 here, and then 2. So we go down to 2 here, and we go and we meet where they meet, the 2 lines meet, the upper and lower. You'll notice how it's a capital B character, and that's exactly what that value has displayed on the screen. So you see how that relates to the chart that we have here, which is available in the data sheet for the HD44780 LCD. And so you just essentially go and you map out which characters you want to have displayed, and you assign that specific hexadecimal value within the VHDL code, and that will dictate which character is being displayed. And so eventually what you can do is there's areas of memory within the RAM that you can send your own character data and pixel information, so you can create your own graphics or your own custom characters. And that'll be a future instructional video that I'll put together to show you how to do that. So anyhow, that's pretty much how the signals are interpreted. And so again, remember that this is a true scan off the logic analyzer. So now we're going to go and we'll check out the VHDL code that I wrote to create this specific sequence, initialization sequence, and the character data. So we'll go and look at the VHDL code, and we'll compare it to this waveform, so that you can understand how the code works and how it creates these specific signals.